Hi there. I hope you are doing okay. By the way, I'm Alexis Rodriguez. Today, I will discuss about gas chromatography. Here's the outline of my presentation. To begin, let me start with a short introduction. The concept of gas-liquid chromatography was first enunciated in 1941 by Martin and Singh, who were also responsible for the development of liquid-liquid partition chromatography. More than a decade was to elapse, however, before the value of gas-liquid chromatography was demonstrated experimentally, and this technique began to be used as a routine laboratory tool. In 1955, the first commercial apparatus for gas-liquid chromatography appeared on the market. Since that time, the growth in applications of this technique has been phenomenal. Currently, several 100,000 gas chromatographs are in use throughout the world. Now, let's dig deeper into the working principles behind gas chromatography. In performing a gas chromatographic separation, the sample is vaporized and injected onto the head of a chromatographic column. Elution is brought about by the flow of an inert gaseous mobile phase. The various components are separated inside the column. The detector measures the quantity of the components that exit the column. Gas chromatography can be classified into two modes: gas-solid chromatography and gas-liquid chromatography. Gas-solid chromatography is based on a solid stationary phase, in which retention of analytes occurs because of physical adsorption. Moreover, gas-liquid chromatography finds widespread use in all fields of science, where its name is usually shortened to gas chromatography, or GC. This presentation will mainly focus on gas-liquid chromatography, as the former is only considered for limited applications. Gas-liquid chromatography is based on partitioning of the analyte between a gaseous mobile phase and a liquid phase immobilized on the surface of an inert solid packing, or on the walls of capillary tubing. Now, let's discuss the components of a typical GC system. Around 50 instrument manufacturers offer about 150 different models of gas chromatographic equipment, at costs that could vary from $1,000 to over $50,000. The basic components of a typical instrument for performing gas chromatography are shown in the diagram. It simply consists of a carrier gas system, a sample injection system, column and the column oven, a detector, and a data acquisition system. The mobile phase gas in gas chromatography is also called the carrier gas, and it must be chemically inert. Helium is the most common mobile phase, although argon, nitrogen, and hydrogen are also used. These gases are available in pressurized tanks. Pressure regulators, gauges, and flow meters are required to control the flow rate of the gas. In contrast to most other types of chromatography, the mobile phase does not interact with molecules of the analyte. The only function of the mobile phase is to transport the analyte through the column. For high column efficiency, a suitably sized sample should be introduced as a plug of vapor. Slow injection, or oversized samples, cause band spreading and poor resolution. Calibrated microsyringes are used to inject liquid samples through a rubber or silicone diaphragm, or septum, into a heated sample port, located at the head of the column. For the most reproducible sample injection, newer gas chromatographs use auto-injectors and auto-samplers. The columns in gas chromatography are of two general types: packed columns, or capillary columns. In the past, the vast majority of gas chromatographic analyses used packed columns. For most current applications, packed columns have been replaced by more efficient and faster capillary columns. Chromatographic columns vary in length, from less than 2 meters to 60 meters, or more. They are constructed of stainless steel, glass, fused silica, or Teflon. In order to fit into an oven for thermating, they are usually formed as coils having diameters of 10 to 30 centimeters. Column temperature is an important variable that must be controlled to a few tenths of a degree for precise work. Thus, the column is normally housed in a thermostated oven. The optimum column temperature depends on the boiling point of the sample, and the degree of separation required. Roughly, a temperature equal to, or slightly above the average boiling point of a sample, results in a reasonable elution time, around 2 to 30 minutes. For samples with a broad boiling range, it is often desirable to use temperature programming, whereby the column temperature is increased either continuously, or in steps as the separation proceeds. This figure shows the improvement in a chromatogram, brought about by temperature programming. Chromatogram A and B are both isothermal, while chromatogram C is programmed. Dozens of detectors have been investigated and used, with gas chromatographic separations. The ideal detector for gas chromatography has the following characteristics. 1. Adequate sensitivity. 2. Good stability and reproducibility. 3. Linear response to solutes that extends over several orders of magnitude. 4. A temperature range from room temperature to at least 400 degrees Celsius. 5. A short response time that is independent of flow rate. 6. High reliability and ease of use. 7. Similarity in response toward all solutes or, alternatively, a highly predictable and selective response toward one or more classes of solutes. 8. Non-destructive of sample. Needless to say, no current detector exhibits all of these characteristics. These are some of the more common GC detectors. The flame ionization detector or FID is the most widely used, and generally applicable detector for gas chromatography. With the FID, effluent from the column is directed into a small air hydrogen flame. Most organic compounds produce ions and electrons, when pyrolyzed at the temperature of an air hydrogen flame. These compounds are detected by monitoring the current produced by collecting the ions and electrons. The thermal conductivity detector, or TCD, which was one of the earliest detectors for gas chromatography, still finds wide application today. This device consists of an electrically heated source, whose temperature at constant electric power depends on the thermal conductivity of the surrounding gas. The electron capture detector, or ECD, has become one of the most widely used detectors for environmental samples, because this detector selectively responds to halogen-containing organic compounds, such as pesticides and polychlorinated biphenyls. One of the most powerful detectors for GC is the mass spectrometer. The combination of gas chromatography and mass spectrometry is known as GCMS. A mass spectrometer measures the mass-to-charge ratio of ions that have been produced from the sample. The last major component of the GC system is the data acquisition system. The data system is used to translate electrical signal generated by the detector into a peak chromatogram. The area of the peak is representative of the concentration of the analyte. The most commonly used devices for generating the chromatogram and report are the integrator and the personal computer. In general, gas chromatography may be used for both qualitative and quantitative analysis. Gas chromatography is widely used to establish the purity of organic compounds. Contaminants, if present, are revealed by the appearance of additional peaks in the chromatogram. The areas under these extraneous peaks provide rough estimates of the extent of contamination. The technique is also useful for evaluating the effectiveness of purification procedures. In theory, GC retention times should be useful for identifying components in mixtures. Although a chromatogram may not lead to positive identification of the species in a sample, it often provides sure evidence of the absence of species. Thus, failure of a sample to produce a peak at the same retention time as a standard obtained under identical conditions is strong evidence that the compound in question is absent. Gas chromatography owes its enormous growth in part to its speed, simplicity, relatively low cost, and wide applicability to separations. It is doubtful, however, that GC would have become so widely used were it not able to provide quantitative information about separated species as well. Quantitative GC is based on comparison of either the height or the area of an analyte peak with that of one or more standards. If conditions are properly controlled, both of these parameters vary linearly with concentration. Now, let's discuss the applications of GC. The list of gas chromatographic applications is very extensive. The following is an example list of application. Food analysis. The food industry relies on the technique of gas chromatography for several applications, including the quantitative and qualitative analysis of food, the analysis of food additives, components of flavor and aroma, and the detection and analysis of contaminants, such as environmental pollutants, pesticides, fumigants, and naturally occurring toxins. Quality control. Manufacturing relies on gas chromatography for quality control. Companies that produce cars, chemicals, and pharmaceuticals, in particular, are big adopters of the technology. Research. Gas chromatography is fundamental to many research areas, in particular, for the analysis of meteorites and natural products. Scientists use gas chromatography to analyze the composition of meteorites that fall to the Earth. Forensics. For many years gas chromatography has been used in forensic science. Mostly, it is used to deter circumstances of a person's death, such as whether they ingested poison, or consumed drugs or alcohol in the hours prior. Measuring air pollution. Air pollution has become an increasing problem in recent decades. Gas chromatography is being used to combat the problem by monitoring the levels of harmful pollutants in the air, so that scientists can visualize where air pollution is more concentrated, and how this changes throughout the day and the year, to develop effective preventative methods. Blood alcohol analysis. Gas chromatography has been used since the 1950s to detect blood alcohol levels. Since then, it has continued to be used to detect how much alcohol a person has consumed, to help gauge how impaired their normal functioning may be. Now, let me show you how to operate a GC system.
So to use the GC, we're going to click User. And then look at this icon right here called GC Solution. That's the one we're going to use. But first, we have to turn on these gas canisters. The first one is the air, then the nitrogen. Finally, we'll turn on the hydrogen. Next, Adam's going to turn on the instrument with a button located on the side. As you can see, all three lights are green. Next, we're going to open the software. We'll click this little icon here. It looks like the instrument and it's under the 1. We'll just click OK. That's fine. Click top. Then we'll go to instrument parameters. And then click system on. It says download the instrument parameters. We'll click OK. At this point, the instrument will try to heat up and ignite. All you have to do is wait. Okay. So your first step is going to be to go to instrument parameters, and you can go file, new method file. And that sets up a new method file. So then what we're going to do is we're going to go to the column. This is the column that's in there. You don't need to change anything there, so that's fine. That's okay. You can set the temperature of your detector. Usually we keep ours at 200 degrees Celsius, so we'll leave that there. This is where you determine your column tab, and it's right here. So it starts off at 25 degrees, and you can hold it at 25 degrees for, let's say, 1 minute, and hit enter. And then we want it to heat up to 50 degrees. So we type in 50, as you can see there. And then this is the rate per minute that it's going to increase. So let's say we want it to go up 5 degrees every minute. It's going to stay at 25 degrees for 1 minute and then go from 25 to 50 over a course of 5 minutes, which is how we get our total program runtime of 6 minutes. Once you've set all these parameters, to the way you want it. Temperature, the start temperature is going to be 25 degrees. You just click this download button, and it's going to download that method to the instrument. Next, we're going to show you how to run a sample. So you go batch processing, batch table wizard, load method file. You select the method file you just created and saved. I didn't show you how to save it. Click next, standard unknown. We want standard only. Click next. We're going to go ahead and click under standard sample vial. It's going to be 0 because we're doing manual injection. Click next. This is really where you can do whatever you want. You can name the file. So we'll name this one test. And then for report format file, we're going to go to GC solution. And then we'll click sample. And then we'll scroll over to method symbol. And that's going to be our report file format. And then we'll click finish. Now we're ready to go. So what we're going to do is we're going to hit start. Save current batch file. We do. You type in the same name as earlier. Save. Yes. Save. Okay. And with our sample, we're going to inject it in the injector shown right here. So we put in, now we're going to put in 1 microliter. Alright. Once it's in there, we're going to click start on here. And then we immediately have to go to injector and change the temperature. Just go to set. This is why you can't do it. Set line config, and then we're going to go to line 1 and click enter, and then click return. And now your sample is running. After the experiment is completed, it'll come up to a file like this. And so what you can see here is we have our chromatograph. We have acetone, ethanol, butanol, 3 peaks. To use this data, our first step is going to be to go to data analysis, manual peak integration, And then we're going to remove all the peaks. So you click here, and you click here, here to here, and it removes all the peaks. Then we're going to insert peaks, so we can go from here to here, and then we'll insert another peak from here to here, and then we'll insert a third peak from here to here. And so those are our 3 integration values, and then you go report in data, and it sends you a thing like this. Next we're going to insert a table right here, and click OK. And what you can see here, I don't know if you guys can see it. Let me try and zoom in. There you go. Can you guys see that? So the table we just inserted, we have our 3 peaks, 1, 2, 3, and we have the area and their retention time shown. This is the integration area, and you can use this to compare them. So then we go back. And so we know peak 1, peak 2, and peak 3. Alright? To shut down the instrument, all you do is you go to, this is the report file, so we don't need that. You go to instrument parameters, and you go system off. And that's going to shut down the software, so you can just hit X. You want to save your method file. You just hit X there and start log off. And then to shut the instrument, all you have to do is flip the button and then make sure you close the tanks.
At this juncture, we'll discuss an article involving the use of GC. Here is the outline for the discussion of the featured article. So, let's talk about green coffee. Current food industry trends include the production of new functional foods, so far known as superfoods, with pro-health properties through the introduction of components with antioxidant or antimicrobial activity. Recently, green coffee has been introduced as a food supplement regarding its functional and antioxidant activity, since it contains phenolic compounds and caffeine. On the other hand, caffeine is a stimulant, which has different health effects concerning stimulation of the central nervous system, and can produce restlessness, headaches, and irritability. Large amounts of caffeine consumption can cause physiological and psychiatric dependence. The European Food Safety Authority mandates that energy drinks with over 150 parts per million caffeine content should be labeled as having high caffeine content, and the exact amount should be indicated. This rule excludes tea, coffee, and cocoa. Many different modern analytical methods are proposed in the literature for the determination of caffeine in coffee samples. Caffeine is usually determined in coffee samples by the use of liquid chromatography, combined with different detectors, such as UV or mass spectrometers, and rarely by gas chromatography. Sample preparation before this analysis is usually very simple and contains only hot water extraction, filtration, and dilution steps. However, liquid chromatography sometimes demands the use of complicated mobile phases, as well as careful pH adjustment procedures which are both time and cost-consuming. Thus, I present this study entitled, Development of a Rapid Method for the Determination of Caffeine in Coffee Grains, by GCFID, a fully validated approach. It was published by Pazias et al. In the journal Antioxidants, in 2017. The aim of the current study was to develop a rapid, accurate, precise, and low-cost analysis for the determination of caffeine in coffee grains by GCFID without using an internal standard. For this reason, special precautions for the accuracy and the precision of the method were taken and presented for the first time. Finally, a whole validation protocol guide, according to the ISO 17025 accreditation standard, is presented. To start the experiment, 3 different qualities of coffee grains were purchased from the local markets in Lamia, Greece. From each category, 3 different samples under the same brand name were purchased in order to estimate the average content of each sample. Samples were then homogenized in a mortar. Then, half a gram of the homogenized coffee grains were extracted with 10 milliliters of ultra-pure water by heating for 15 minutes at 100 degrees Celsius. The samples were then back extracted using 10 milliliters of dichloromethane. The dichloromethane extracts were then filtered, and 1 microliter was injected into the GC system. The method was fully validated, according to ISO 17025 requirements, and European Commission regulations. Parameters, such as matrix interference, repeatability and reproducibility, accuracy, limit of detection, limit of quantification, and uncertainty of the method, were all checked. All measurements were performed with a Shimadzu GC 2010 Plus GCFID system, using an Agilent DB1 column. The optimized conditions were: injection volume, 1 microliter in split mode 50:1, injector temperature, 280 degrees Celsius, carrier gas, helium at a constant flow of 1.8 milliliters per minute, and detector temperature, 300 degrees Celsius. The initial oven temperature, 100 degrees Celsius, was held for 2 minutes, then programmed to increase at 8 degrees Celsius per minute, to 180 degrees Celsius, and finally programmed to increase at 10 degrees Celsius per minute, to 250 degrees Celsius, where it was held for 0 minutes. As reported in the study, here are the superimposed chromatograms of caffeine, in a standard solution, and in a coffee grain sample. The method was fully validated, according to ISO 17025 requirements, and the European Commission regulations. The accuracy, as provided by recovery experiments, was higher than 93%, and the precision, as provided by the percent relative standard deviation under reproducibility conditions, was lower than 5%. The developed and fully validated method was applied for the determination of caffeine in different Guatemala coffee grain samples. The mean caffeine content was found to be equal to 1.3% weight over weight. In the current work, a rapid, precise, accurate, and low-cost method for the determination of caffeine in coffee grains was developed without using an internal standard. The method was considered as fit for purpose, according to the requirement of ISO 17025 and European regulation concerning the aspects for the accurate development of analytical methods. The Guatemala coffee grains analyzed by the developed method was found to contain a high amount of caffeine, and can be used as functional food, but it may also lead to depression and anxiety. We have come to the last part of this presentation, to discuss the advantages and disadvantages of using gas chromatography. Here are some of the advantages of GC. Extremely high resolution or separation power, unmatched by most other techniques. Easy to couple to other analytical techniques for sample identification, such as mass spectrometer. Can be used with really minimal amounts of sample, in micrograms or less, with detection limits in the order of parts per billion or less, in some instances. Relatively inexpensive and modular. It is easy to add, or take off, different kinds of injectors and detectors, for different purposes. It can be automated with auto-samplers. These are few disadvantages of GC. The sample must be volatile, not necessarily at ambient temperature. It is okay if it is volatile at 250 degrees Celsius. Recovery of separated sample components is very hard or impossible. Detectors are generally destructive. Well, that's all for today. I hope you have learned something new from this presentation. Thank you for watching, and see you again next time.